Matt Duff. I will be presenting on the absorber water flow system for the Lavender Team. Just an outline of what I'll be going over, some background and introduction to the absorber water flow system, the SSOC information we received, as well as the step response, and also our sign response experiments, modeling, and conclusions. This is just the lab view display of the absorber water flow system. As you can see, it's both water flow and airflow. And this is a picture of some of the meters used to measure the actual water speed, the flow meter in particular. On the left side, you see 2 rotometers and a manometer, which are just kind of redundancies. Here's just a simple system diagram. It begins the input function, depending on what it is, and then the output and water speed. Oh yeah, and the input, while there's several variables depending on which function you're using, the main one is the percentage in which the valve is open. We run the duct cooling system at the beginning, so we do not have SSOC or step data for this, but Dr. Henry was nice enough to give these to us. Here you see the SSOC curve. As you can see, it's not a perfectly straight line, so there are inconsistencies. Here is the step up example, and that we were given values for gain of 0.21 and dead time at 1.9 seconds and pow for 2 seconds. And the step down is pretty much the same. I believe dead time was off by 0.16. Yeah, it's 1.9 and the step down. And the next thing we did was the sign response experiment, and this just sort of give you an idea of what you get to control as you input. Here is just an example readout that you get from actually running the experiment. You can see it's pretty hard to distinguish the output, the sinusoids. Once you import the data into Excel, you can kind of see it a little better, how the curves actually go with it. You can see the lag from the output right behind the input. And here's just sort of a analysis how you do it. To get the data to make the Bode plot. Your delta C is your change in, or your amplitude of your input, and your delta M is your output amplitude. So the delta M is the input, delta C is the output. And to get the amplitude ratio, you just divide delta C over delta M. And to get the phase angle, you take that little t, which is the peak of the input, to the peak of the output, and you divide that by the big T, which is the period of the input, multiplied by 360. And once you do that for all the frequencies, you get a nice table like this. And as you can see, amplitude ratio decreases as the frequency goes up. And this can be better seen on a Bode plot. And here's the top half, which is amplitude ratio versus frequency. And you can get your values for gain by the asymptotic value of the amplitude ratio. Your ultimate frequency is, you can't see it down on this part, but it's where the phase angle is negative 180 degrees. Your order, which this one's 1, is the negative slope as the amplitude and frequency graph come together. And 1 over KCU is just the amplitudinal value at FU. And here's the bottom half of the Bode plot. just phase angle versus frequency. And here were our experimental results for the sine response. And K is in pounds per minute per percentage, 0.3, orders 1, ultimate frequency 0.2. You guys can read that. For the model data, after we inputted the equations into Excel and sort of messed around with the parameters, this is the best we could get. The points of actual experimental data, while the curve is the model. And you see at lower frequencies, it's a little closer than once you get above 0.2 hertz, it kind of gets away from us. Here's the lower half of that same graph, and it's pretty good. You know, again, the lower frequencies are better, match up better anyway. Here are the actual parameters of the modeling system versus the experimental. You can see they're pretty close. And here are the final results with all the model amplitude ratio and phase angle versus the experimental amplitude ratio and phase angle with uncertainties included as well.